Introduction to Quantum Circuits. I am going to review the IBM Q Experience introduction guides. Now, I'm gonna try to approach that more from a review perspective, basically because I have already gone through the basic concepts, and so it wouldn't be it wouldn't be an interesting video just me reading through that stuff. But I think this I kind of basically went through the overview of the topics, and I will obviously leave aside things which I don't consider they are relevant for building intuition, like the universality of quantum computation. I think almost every guide out there talks about that, and don't get me wrong, feel free to dive into this if you think that's useful for you. I don't think it's useful in general for building intuition. It just dives a bit more into the mathematics of why what's a universal set of quantum gates, and why is that a mathematical proof of why is that correct. Was that a true statement? But I'm mostly interested in. So let's see what we have here. I'm going to put some color into this. I'm mostly interested in how does the guy get started. See some interesting stuff already here. I'm definitely interested in the the quantum gates part. So I think I know what to expect a little bit when seeing this, but let's see. Probably that's not going to be interesting for the building intuition. So talking about the physical systems. Although I get it that at the stage in which quantum computing is now knowing a bit of the physical limitations of your device of the device you would be running your algorithms on makes sense. But I think. Let's see what happens here. Basic circuit identities. This doesn't seem to scroll correctly, but I think it's because I have the pen. Anyway, so let's get started. If you think quantum mechanics should sound challenging, you're not alone. The quantum objects can seem random and chaotic at first. They just follow a different set of rules. Once we know what the rules are, we can use them to create new and powerful technology. Cool. So I like that approach, right? Exploring what the rules are. And that's a quantum circuit to calculate 1 plus 1. That's an interesting way to introduce someone to quantum computing, because that's definitely not something that a quantum computer is the best for, but I guess it illustrates the concept. And so kind of I guess we'll go through that later in the guide, but I assume that those are like, this is the 1 and 1 you're trying to add up, and here's what you're trying to measure. So so this would be the core of what happens, right? And so you do a control knot, so you're working on this qubit, and I guess that's kind of where you put the carry. So what you carry when you add 1 plus 1, it's 2, because then in binary that's 1 0, right? So yeah, and that's probably what that thing here, which seems to be like a double control knot, is doing. Cool. To get you started, what you already know about what is a beat. Okay, so it really goes. So the guide really goes down back to like what a beat is. So this chapter is intended for the broadest possible audience. Okay. Contributions. Exclusive playing games. Yeah, I think it's pretty generic. There's any math. That's interesting. You won't see any math that you didn't learn before you were age 10. let's check that. Okay, the atoms of computation. So let's go to the next one. How to switch back to this? So I guess that's the next chapter here. Yeah. The atoms of computation. Oh, let me clean that up. Wipe screen. So the atoms of computation. Programming a quantum computer is now something that anyone can do with the comfort from their homes. Blah blah blah. Splitting information into bits. So I think it's going to be answered by making comparisons to digital computers. Unfortunately, most people don't actually understand how digital computers work either, and that's true. Okay, I think I'm going to. I have the impression, just because of I'm seeing here those. I think that's way too basic, as in like introducing what a decimal system is, what a binary system is. It seems like that's the case. So I'm going to skip that because my assumption is that if you're watching these videos, you're interested in the practicality of quantum computing from a development perspective, a programming perspective. So you sort of should know these things. But go ahead and read that. I think it's a fairly nice way. I think it's a fairly nice way to introduce someone to really the very basics, and doing that with the quantum composer, with the circuit composer. So pitches, oceans, historical reasons of the circuit, blah blah blah, visualizations. Qubits and numbers 007. The measure operation is immediately applied to the qubits, which simply extracts the qubit number 0 and 1. Qubits are always initialized to give the output 0. We know that. So it's always going to be zeros. Okay, so it goes through the basics, explaining you what that visualization is, which basically is the probability of reading out that state. Okay, now I see it adds a next gate, which is basically a NOT. So now you've got that state, and yeah. Comes okay, so it explains you basically how many possibilities you've got in an 8-bit computer, if that was a classical computer, right? Remembering how to add. Okay, so it goes through the basics of how does like the adding algorithm work with decimals. 4 plus 3 it's 7, 5 plus 1 is 6, so you've got the 7 and the 6 here. Okay, and then you're going to go through the carry. Okay, yeah, the basics. Okay, now how to do that in binary. I mean, I don't know. Maybe there is some. Maybe because I'm reading through that pretty fast. Maybe there's something in here that is like a good insight, but it seems too much of a really starting from scratch. Like, but I think it's a good exercise. Even if you know all that, I think it's a good exercise. Finance is yeah, of course. So that's what is this and that. It's this is 11. This is 1 1. Decimal adding. Oh, okay. That can be let's adding with the composer. So now we're gonna go through that circuit that we saw at the beginning. Maybe that's helpful. So you've got the input bits here, as I said. Then you've got the output, the extracting in here. So the 2 bits we want to add are encoded 0 and 1. The above example encodes 1. So to find the solution 1 1. So basically, this is just an example, and you're encoding your inputs, right? So there's no here like input management or whatever. It's always going to be 1 plus 1 in this case, because you're hard coding the input. The dashed lines in the image are just to distinguish the different parts of the circuit. That's helpful. This line here and this line here. Okay, so you can add that. Barriers. Yeah, I think I've used that in the past. The basic operations of computing are known as gates. We have already used the NOT gate, but this is not enough to make our half adder. We could only use it to manually write out the answers, but since we want the computer to do the actual computing for us, we'll need some powerful gates. So let's take a look at what the half adder does. Okay, so now I guess that's what we're going to try to build, right? The rightmost is completely determined by whether the 2 bits. The rightmost bit in all our 4 of these answers is completely determined by whether the 2 bits are adding. We are adding at the same or different. The rightmost, right? So, okay, I see. So you've got a 0 when it's 0 0 and a 0 when it's 1 1, and if you've got a 1 when it's 0 plus 1 or 1 plus 0. To get this part of the solution correct, we need something that can figure out whether 2 bits are different or not. Okay, so that's where the control node comes in, right? Because if you assume that you start with zeros in both sides, so you're basically, so if here you've got a 1 and here you've got a 0, right? Then you're gonna end up with a 1 here, right? Because let's forget about this, because basically this is going to trigger the control knot. But if you've got a 0, if you've got a 0 and a 1, then you're going to end up with a 1 here as well, right? Because you already have a 1, so that's what you want. Those are these two, this and this. Okay. Another way of explaining the control knot. Yeah, I think that makes sense. Try the control knot for yourself. Okay, so basically that's what you're doing here with the circuit. If you set this up, you'll find that the output is 1, 1. We can think of this happening because of either the following reasons. The control knot calculates whether the input values are different. Yeah, I mean, again, that we are getting into how to interpret a gate, right? So here you're sort of trying to, you're doing problem solving, and then you're going one extra mile by saying, like, how you're stretching a bit, like, okay, the control knot is it detects whether something is different or not. I prefer to stick to one interpretation always. And yeah, you can use it sometimes for different things, like adding in this case. But again, you're only able to do that because it's sort of a binary thing, right? Zeros and ones, and the limitations of the binary system allow you to kind of create the illusion of adding by using that type of gates. Okay, good. For a half adder, we don't want to overwrite one of the inputs. Instead, we want to write the result on a different pair of qubits. That's why I use classical ones here. So if you look again at our 4 possible sums, we'll notice that there is only one case for which there is 1 instead of 0. Yeah, so that's this case. It's the only case in which we carry a 1, right? And this happens only when both bits are 1, and I guess that's where that's where this kind of control knot that's controlled by two qubits applies, right? So in case of both are 1, then this is then flipped into a 1. And this is called Toffoli. Interesting. For this, we need a new gate like C naught, but controlled by 2 qubits instead. Okay, it's pretty interesting. I think it's a pretty interesting way to get you used to the circuit, and to the concept of computing, right? So I think it's maybe not super necessary to actually help you build quantum intuition, but because the first chapter literally has nothing about the quantumness. It's just helping you get started with computing in general and beats, etc. Okay, interesting, perfect. And I think that for that matter, I'll just leave this here exactly.